In this video, I'm going to go over decay and bombardment. There are two types of nuclear equations. The first two are going to be decay problems, and when a radioactive sample is going through decay, what it's telling you is that nucleus is unstable. It doesn't have the right mix of protons and neutrons, and it is going to go through a type of decay that is going to make it more stable. So since this thing, thorium-232, and the 232 is telling you the mass number, since it is unstable and it's going through decay, in this case alpha decay, that is going to be the only thing to the left of the arrow. And anytime you see this word decay, that's telling you that this is going to be the case where you only have one thing to the left of the arrow. It's just that thing breaking apart to become something more stable. In this case, it's ejecting an alpha particle. So an alpha particle is a helium nucleus for the most part. So you can write it as mass number 4, atomic number 2, right, because of the nuclear symbols, the atomic number is on the bottom, and you could use the symbol He for helium. The other way you could do it is 4 up top, 2 on the bottom, so the mass number and the atomic number, and you can do an alpha symbol. It doesn't matter which one you pick. These things are interchangeable. You can just use one of them. Now, when you're doing this, you want to pay attention to the mass number and the atomic number, right? Mass is still conserved in nuclear equations. So you start off with this mass number of 232. Well, 4 of it is taken up in the alpha particle. So the other product is going to make up the other 228. The atomic number of 90, 2 of it is taken up in the alpha particle, so the other 88 is the other product. And you find 88 on the periodic table, and it is radium. Right, the masses, double check your work, the masses all add up, the atomic numbers all add up. It's alpha decay, you have an alpha particle as one of the products, and that's what's going to happen. Thorium-232 will eject an alpha particle and become radium-228. For the next one down, it's saying beta decay of uranium-239. So we can write uranium-239, find uranium on the periodic table, it is atomic number 92. Since it's a decay, that is the only thing to the left of the arrow. Now, beta decay is an odd kind of thing. What happens is that one of the neutrons in the nucleus of this uranium-239, since that is an unstable mix of protons and neutrons, in this case, a neutron spontaneously converts into both a proton and an electron. And if you think about what's going on there for the mass, a proton and the neutron have pretty much the same mass, and an electron has essentially no mass. So when the neutron changes to a proton and electron, the mass is conserved at that point. And the other thing is a neutron is neutral. It has a neutral charge, so when it changes into both a proton and an electron, the charge is still neutral. Right? So mass and charge are conserved when that happens. But now you have this electron that is shot out of the nucleus at very high speeds. So what happens is you eject a beta particle, which is essentially an electron. Now again, you can either use the beta symbol here, or you can put a lowercase e for electron. It doesn't matter which one you pick. Right, so the beta particle gets ejected about, well, 0 mass because it's an electron and a -1 charge. It also says gamma radiation is released. Now gamma is not a particle, it is just pure energy. Very, very high energy, which is why scientists are concerned with it, but it has 0 mass and 0 charge. So mathematically, it doesn't do anything to the problem we're trying to do, but you want to definitely make a note of gamma radiation. So we do the same math that we did. You start off with 239 on the left for the uranium. You're getting 0 from beta, 0 from gamma. So whatever this other particle is, it has to have a mass of 239. You started off with uranium-92. Well, you end up gaining a proton because a neutron changed into a proton and an electron, and the electron got shot out of the nucleus. So what you end up getting is 93. And if you think about the math, 93 plus a -1 gives you 92. Right? Because that's what you end up doing. You add the products, like here, 2 plus 88 is giving you 90, and that's what equals to the left-hand side. Well, here you have 93 plus a -2 equals 92. So you find, for this one, you find 93 on the periodic table, and it is Neptunium, Np. and that is beta decay. So one of the things that throws people off, if you're going too fast, you have to pay attention to this being a negative, because you're actually going to go up in atomic number. It's very easy to miss that if you go too fast. Now, the next one down is a bombardment reaction. And this is going to be different. We would have to see some form of the word bombardment, or bombarded, or bombards, something like that. It's saying uranium-238 is being bombarded by a neutron. It's going to yield a beta particle and another product, right, the equation. So a neutron, it has a mass of 1, but it has no charge. And it gets a lowercase n for the symbol. And we want to write uranium-238. Uranium on the periodic table is atomic number 92. Where it says yields, that's where the arrow goes in. A beta particle, again, is an electron. Again, this is one that you could do two different ways, and it doesn't matter which way. So we have to do a little bit of math here. The stuff on the left is going to add up to the stuff on the right added up. So 238 plus 1 is 239. You're not getting any mass from the beta particle, so this product has to have all of that 239. You have a 92 as the atomic number on the left. You have a negative 1 here. So what added to negative 1 gives you a 92. It has to be 93, which ends up being Neptunian. So make sure you double check with the math, but those are alpha decay, beta decay, and bombardment. Pay attention to the wording, because that's going to give you an indication of what type of problem it is.